pretty fast prover. The downsides are the verifier costs are somewhat high. Although, well, the proof size is actually like for practical instance sizes like smaller than fry proofs. But I think I calculated the gas costs, and since it involves a lot of curve operations, it would be more gas intensive than fry proofs on chain. So I think the goal is to use Hyrax as the polynomial commitment, but do some amount of composition to get the verifier cost down. And that's basically, there's a pretty brief description of something we call SONA in the Lasso paper, which basically says, well, just compose Hyrax with Nova to get the verifier cost down. And we'll have to see how things go, just to make sure that the composition doesn't become a bottleneck for the prover. But I don't believe it should. It might take a little bit of engineering to ensure that.
Oh, okay, got it. So currently, there's no plan to implement other.
No, I would not say that. So there is, I do want to integrate like a whole bunch of choices of polynomial commitment. And I think if for whatever reason, somebody doesn't want to do composition, they'd probably want to use some sort of multilinear analog of KZG, whether it's, the new like zero morph commitment scheme or something like that. So no, I think we'll integrate a bunch. But my hope is that, like, generally, I think what people should target, conceptually, and also I think it should work out concretely with enough engineering, is the polynomial commitment schemes with the fastest prover tend to have like square root verifier costs, which is like larger than you would like. But you can bash those costs down through recursion, and all you have to do is make sure that the verifier as a circuit is like, is sufficiently smaller than the original circuit you were proving something about, that the composition is not a bottleneck, and square root should be plenty small for that. So yeah, I think let's see, probably Hyrax is like the fastest prover elliptic curve based polynomial commitment scheme. So that's why I want to try to use that. I do have some work in progress to try to make this stuff, the Lasso Jolt stuff, more attractive, even when using like hashing based commitment schemes. And there, I think, Breakdown and Ligero are pretty attractive, and those have square root costs. And you'll actually see some projects switching over to Breakdown and Ligero soon. I think they're even public about it now. So I do think there should be a variety of polynomial commitment scheme options integrated into the code base.
Wait, why are you saying it's elliptic curve based? Is it the Peterson stuff? You mean the?
So Hyrax is based on elliptic curves. It basically the prover does a bunch of MSMs as the commitment, and we're starting with elliptic curve based commitment schemes because Lasso and Jolt are like very obviously a significant step forward in performance for such commitment schemes, because they only have the prover commit to small field values, unlike really all like prior work. And that's good for more than an order of magnitude speed up in prover time. So it sort of makes sense to start with elliptic curve based commitment schemes, with Hyrax being, amongst the fastest for the prover. Just because it's they're so like unequivocally a big step forward with those schemes. But I think that Lasso and Jolt are also a step forward with hashing-based commitment schemes as well. But I think there's a little bit more work that can be done to make that clear, because people really like to use the hashing-based schemes over small fields. So basically, the extra work that I have in progress is to make if you're not careful about how you implement the prover in SumCheck when you're working over small fields, the field work for the prover in SumCheck can become a bottleneck. In some cases, it really depends. If it's not a bottleneck, then I think Lasso and Jolt are already better than existing work. And if it is a bottleneck, then it's not clear. So I have some work in progress to try to speed up the SumCheck prover when working over small fields. Did all of that make sense?
The MSM in Hyrax is different with KZG.
Yeah. So in KZG, the prover does one big MSM. In Hyrax, the prover does something like square root many MSMs, each of size square root, which is actually slower by a factor of 2 for the prover. It's sort of the opposite of what you get for FFTs. Like FFTs are like n log n time, but MSMs, because of the Pippinger speed up, you actually it's like n times security parameter over log n. So you divide by log n instead of multiply by log n. So yeah, you're actually right. Yeah, so maybe I should explain why I say Hyrax is amongst the fastest for the prover. So let's see.
The group is different, right? Because in Hyrax you just need a group where discrete log is hard.
Yeah, so that's one reason. Yeah, so KZG you need a pairing friendly group. Hyrax you don't. And the really nice thing about Hyrax is the prover to compute an opening proof does literally no cryptographic work. And so yeah, in Lasso and Jolt, we essentially ignore the cost of computing a polynomial commitment scheme opening proof in our accounting, and this is justified for several reasons. So you cannot all ignore it if you use certain polynomial commitment schemes. In particular, bulletproofs has very, very slow opening proofs, and they can easily be the bottleneck in Lasso or Jolt if you were to use bulletproofs. KZG is better opening proofs than bulletproofs, so I think it probably would be okay to ignore the cost of an opening proof using KZG. But with Hyrax, like, you definitely can ignore that cost. It's like, opening proofs for the prover are basically nothing. So that's a nice thing. It just makes the accounting of charging nothing for the opening proofs clearly justified. But in general, these opening proofs have very nice batching properties, and so the prover can commit to a whole bunch of polynomials over the course of the protocol and only do a single opening proof. So I think like probably the only polynomial commitment scheme where you really can't ignore the cost of opening proofs unless you're doing a ton of batching is bulletproofs. So anyway, just to summarize, a benefit of Hyrax over KZG is no pairings needed. A downside is by doing many MSMs instead of one big one, you actually might get a factor 2 slowdown for the prover. But another benefit of Hyrax is the opening proofs are like, almost instantaneous, definitely a low order cost for the prover in Hyrax. So there are lots of trade-offs from different polynomial commitment schemes, and that's why I actually do want to integrate a bunch of different choices with the library, but I'm sort of personally most bullish on Hyrax. We just probably want to compose it with something else to get the verifier cost down a bit. Oops. Sorry. I might have to just I think I'm getting a call from daycare. Let me see if my no, okay. I will just tell my wife. Apologies. Just give me 1 second. Then did not. This is the one number I can't actually just ignore. Which one is this? Okay, but I don't actually think it's that urgent. So let me just send her the number. Thank you for bearing with me, and I apologize for the interruption. Uh, okay. Okay. Sorry about that. So where were we? Yeah. So lots of trade-offs with the polynomial commitment schemes. So I do want to integrate many, but I think as long as we manage to get composition implemented on Hyrax with its square root costs, without it being a bottleneck, I think that's going to be a pretty attractive choice. So just wrapping up the discussion.
If you have a list and if you have a polynomial commitment scheme that's like low priority, I might be interested. Like if others don't, if others are prioritized to like implement Jota and other things.
Okay, yeah, sounds great. I'll definitely keep that in mind, and I bet we can find something worthwhile there. Yeah, thanks for offering, and I'll follow up on that.
Okay, I don't have other questions.
Cool. Anyone else want to ask anything? All right. Okay, so today we're going to finally do Intro to Zero Knowledge. And this sort of leads naturally into discussing polynomial commitment schemes based on elliptic curves, which we actually just discussed several in the Lasser Jolt question. We'll sort of build up to such polynomial commitment schemes and how they work in pieces. So we'll start with a basic building block called sigma protocols. And these are very simple. They're only 3-message protocols that like only very specific problems are solvable by sigma protocols. But then sigma protocols can be used or generalized to give these full-fledged polynomial commitment schemes that underlie many of the most popular snarks today. So that's kind of what to expect in the coming weeks in terms of topics. So today we're just going to cover like what is zero knowledge, and just like one example, which is not a practical example of a zero knowledge protocol. Then we'll start talking about these sigma protocols. Along the way, we'll discuss in detail how people render snarks zero knowledge. And so today we're going to see a protocol that's sort of directly zero knowledge. That it's not a snark. It's not useful for snarks. So the way people render snark zero knowledge is quite different than anything we'll see today. And then we get to all of these discrete log-based polynomial commitment schemes like bullet proofs and Hyrax, which we were just discussing, and KZG and so forth. Okay, so let us talk about zero knowledge. So I guess I'll say the most informal possible definition, and before getting gradually more formal. So a proof or argument is zero knowledge if the verifier learns nothing from the prover, from its interaction with the prover, And in the snark, of course, there is no interaction. There's just a static proof. But in general, argument systems can be interactive. Other than the validity of the statement being proven. And this is essential in some applications, but not others. The quintessential blockchain application is you have some mixing pool, which is trying to convey some amount of anonymity to people who are transacting on chain. So the idea is that anyone in the world can deposit money into the pool and then withdraw the money that they have in the pool. And the way they will do the withdrawals is they will post a zero knowledge proof on chain that they know the secret key that authorized some deposit that has not already been withdrawn and has a balance exceeding the current withdrawal or something like that. And the point is the zero knowledge proof will reveal nothing other than the validity statement being proven, and in particular will reveal no information about which deposit actually had the funds that is enabling them to withdraw. And if the proof actually did leak any information, so the witness here would be like the secret key enabling that authorized the deposit. If the proof leaked any information about that witness, I guess there's sort of two ways you could have problems. If it's leaking information about the secret key, well, you have a real problem where not only might it sort of identify the depository transaction, it might actually leak control over the account that authorized that deposit. But even if it doesn't leak any information about the secret key, but it does leak information about just which depository transaction it was, then the mixing pool is certainly not providing the amount of privacy that it could be. Okay, but for blockchain scaling applications where you're just trying to sort of keep as much computation as possible off chain and you're not worried about privacy or anything, there'd be no reason to have ZK. And in fact, most quote ZK rollups do not use a zero knowledge snark at all, which is extremely confusing. Okay, so let's get a little more formal. So there's a question. It's completely not obvious if you haven't learned about zero knowledge before, how you would formalize the notion that the verifier doesn't learn anything other than the validity statement being proven. The way this gets formalized is with the notion of a simulator. Okay, so let me try to explain this. It'll take a little bit to write this down. Let's see. For any, I forgot that my iPad just completely malfunctions if I plug it in. Sorry about that. For any verifier strategy V, and right, no, if you don't care about ZK, we're used to thinking of the verifier as honest, right? Because the whole point of the protocol is to make sure that the prover isn't lying. And so, the verifier, if you don't care about ZK, has no reason to deviate from, how it's supposed to behave in the protocol. The protocol is there to give the verifier security from a cheating prover. But when you do care about zero knowledge, it actually, potentially makes sense for the verifier to deviate from the prescribed protocol. That is, send messages to the prover it's not supposed to send, in an effort to kind of trick the prover now into leaking information about the witness. Right. So zero knowledge is all about protecting the prover. Let me just take it. ZK is about protecting the prover's privacy. You think of the prover as having some private witness it doesn't want the verifier to learn anything about, other than that the prover knows the witness. And so, Yeah, it's about protection for the prover, which means that now it might make sense for the verifier to cheat and send challenges to the prover that it really shouldn't be sending. So that's why I'm saying for any verifier strategy V, I'm saying like even if the verifier is cheating and trying to like kind of trick the prover into leaking information about the witness, there should exist a efficient. We formalize that as PPT. This stands for probabilistic polynomial time. Just think of it as efficient simulator algorithm. So that's let me just call it S. Yeah, let's say such that the distribution of S, of the output of S. So S is going to be a randomized algorithm. So, you know, its output sort of depends on like the random choices that S makes. And hence, you know, it's for any fixed fixed run of S, there's just some string it outputs, right? But you know, before you fix S's like random choices, what you actually have is like a distribution over possible outputs of S. You know, says, you know, if you choose this random string, S outputs this, you know, this. If you choose this other random string, S outputs this, and you know, in total, you know, there's some probability of each possible output of S. So that, you know, S is a randomized algorithm, so it produces a distribution over outputs. So that distribution should be indistinguishable. If you for now, you can think of it indistinguishable as just the same as, but I'll address that later, exactly what indistinguishable means. The same as what we call the view of the verifier when interacting with the honest prover. So what this is the distribution over what we call transcripts. So a transcript is just a record of the messages exchanged by the prover and the verifier. You know, so it's just a list of the messages they sent each other when, you know, the verifier interacts with the with the honest prover. Okay. Okay, so that's roughly the form, how one formalizes zero knowledge. It's still not completely formal because I haven't told you what indistinguishable means. I think that's really the only. Let's see here. I think that's the only thing that's making this informal right now, essentially. Okay, so this is really a big, you know, bite to piece to bite off here. The definition of simulation. There's a lot going on here, so let's talk about it. So what this is trying to capture is the following. So the prover knows some witness, right, and then, you know, runs this argument system with the verifier. Let's say it's an interactive argument system to try to convince the verifier knows the witness. Okay, and then, you know, we're trying to capture the idea, the guarantee that the verifier doesn't learn anything from the prover's messages to it over the course of this interaction, other than the fact that the prover knows this witness that is claiming to know. And so what's going on here is the simulator S does not know the witness. Okay, and in fact, the simulator S has no information that the verifier doesn't have, right? So, like, you know, moreover, we're requiring the simulator to be efficient. Okay, so anything that the simulator like outputs, in principle, the verifier could have output on its own without talking to the prover, right? Because the simulator is just an efficient algorithm which doesn't know anything extra, you know, that the verifier doesn't know. So the verifier itself could run the simulator. Okay, and what this definition is requiring here is that, you know, the stuffed output by the simulator looks exactly the same as the messages, you know, kind of sent by the prover to the verifier. Okay, so how could the verifier, like possibly have learned anything from the messages the prover sent to it if the verifier could have essentially, seen more, effectively the same set of messages just by ignoring the prover and instead just running the simulator? Right. The verifier, can't run the prover itself because the verifier doesn't know a witness and the prover does, but it can run the simulator because the simulator does not know a witness. Okay, so that's what's going on in this definition of simulation. So it's like it really is like just sort of intuitively obvious that anything output by the simulator must already be known to the verifier, before it even talked to the prover, because the verifier itself, in principle, could just run the simulator. It's an efficient algorithm that you don't need to know a witness to run. And yet the simulator's output looks exactly the same as what the prover sends the verifier over the course of the protocol. So that in turn means the verifier must not be learning anything from the prover's messages. It could have effectively simulated the messages on her own. Okay. Now this is an extremely it's hard to wrap your mind around this because the way I just described it, like your initial reaction really should be like, doesn't doesn't the notion of the simulator, the existence of the simulator, contradict security, contradict soundness of the protocol? Right. So I'm basically saying, like, it sounds like I'm saying the simulator itself can just like output convincing proofs. Right. And the simulator doesn't know a witness. So if it's possible for the simulator to output convincing proofs, isn't it possible for a cheating prover that doesn't know a witness to also output convincing proofs? Like, just have the cheating prover be the simulator. And in fact, there is no contradiction. And that's what I'm now going to, try to say a bunch about for probably take 5 or 10 minutes. But this is exactly the fact that this feels contradictory is why people say zero knowledge is amazing. It feels like magic, feels like it should be impossible. It almost feels like a contradiction, but it's not a contradiction at all. Of course, we have many zero knowledge protocols that are used in practice all the time now. Okay, so let me just pause here though and see if anyone wants to ask a question about the definition of zero knowledge and what the simulator and all of that. Cool. Okay, so I think the best way to see what's why there's no contradiction between the existence of the simulator and security of the protocol actually is probably through Sigma protocols, just because they're sort of the simplest kind of interactive protocol. So a Sigma protocol is a 3-message protocol where the prover speaks first. So the prover will send a message M1 to the verifier will respond with a random challenge R, and the prover will respond with the message M2, and the verifier will, accept or reject based on some predicate. So verifier applies some predicate to the transcript. So the transcript is just M1, comma R, comma M2. Yeah. And okay, that's a Sigma protocol. And let's see what I want to say here. Okay, I'm going to try to say 2 things. The first point I want to make is the following. So if the protocol, so if the Sigma protocol is sound, so that basically means then let's imagine for a second the soundness error was 0. Okay, even though the soundness error will never actually be 0, it'll always be some very small non-zero number, like 2 to the minus 128 or something like that. Let's imagine the soundness error was perfect, was 0. Then if the prover convinces the verifier to accept, then the prover must have been prepared, okay, to answer any challenge R. And even if the soundness error was not zero, like if you just sort of assume that the verifier doesn't get like insanely unlucky, then the thing, what I'm saying basically holds effectively. So, there might be like maybe one or two challenges the prover could have answered, but there's almost no chance the verifier would have actually sent one of those. Basically, if by getting just convinced only once for one R, the verifier actually becomes convinced that the prover was prepared to answer any R. Okay, and so security of the protocol then implies that the prover knows the witness. Okay, and that's why the or how do I want to say this? Okay, that's how the verifier learns that the prover knows a witness, right? We the whole point of the proof system is to confirm that the prover knows a witness. Of course, the verifier is going to learn that, and the notion of simulation and zero knowledge just captures that the verifier doesn't learn anything else. Okay, so but the key point is the verifier only sees the prover's response, so only sees this M2 message for one choice of R. Okay, and so there's that's sort of where the lack of a contradiction between the existence of a simulator and soundness of the proof system is ultimately going to come from. Okay, so what's actually going to happen in these Sigma protocols is they're going to satisfy a property called special soundness. And this says, given two accepting transcripts of a particular form, the form is they share the same first message from the prover, but their verifier challenge differs. So R prime does not equal R. One can efficiently derive a witness. Okay, and that's how we know that's what's going on here in the Sigma protocols. What I said before was soundness is going to tell you that if the prover convinces the verifier even once, then it must have been prepared to basically answer any challenge from the verifier. And then this is saying the special soundness condition is saying if you're sort of able to get responses from the prover in which it's answering two different challenges, you actually could derive a witness. So even the prover knowing the answer to knowing how to respond to two different challenges is sort of enough to guarantee that the prover knows a witness. Okay, and ultimately the way we would wind up getting two transcripts of this form, if you are trying to identify a witness, like kind of pull a witness out of the prover's head, which is sort of what's required in to establish security of an argument of knowledge, the way we would wind up getting these two transcripts is we would run the prover once to get the first transcript, rewind it till right after it sent M1, and restart it again, but now with a different verifier challenge R prime to see how it responds to R prime to get M2 prime. And so that's how you wind up showing that these Sigma protocols are knowledge sound. That is, any successful prover must know a witness. Okay, so to summarize here, the security proof for these Sigma protocols actually, they actually pull a witness out of the prover's head. Okay, and that feels very close to violating zero knowledge. Because obviously identifying the witness is like the biggest possible violation of zero knowledge, and security is demanding that we can actually take the prover and pull the witness out of its head. Okay, so almost feels like a contradiction. What's happening though is the procedure to pull the witness out of the prover's head required running the prover once, rewinding it, and starting it over again, and having the prover, just happily provide you with, that second accepting transcript. Um, and the actual verifier and the actual protocol does not have that access to the prover, right? The actual verifier and the actual protocol, like, kind of only gets to talk to the prover once, you know. So that's ultimately why there's no contradiction. Like, security requires that, like, if you are able to kind of run the prover multiple times and make it, in particular, make it produce two transcripts that share the same first message, then you can identify a witness. But the verifier itself does not have that ability to make the prover give it those two transcripts. It can only get one transcript out of the prover. If you let the verifier kind of talk to the prover again, it's sort of, you're imagining it's talking to the prover from scratch. And so, there's very, very tiny chance that you wind up getting two transcripts of this form. And that's why there's no contradiction. So, like, this, what's called the extractor in the security proof, that pulls the witness out of the prover's head, kind of has, the ability to do things with the prover that the verifier itself doesn't have the ability to do. Okay. I'm going to say one more thing about this. I'm going to explain just a little bit more about how the simulator works in these Sigma protocols. But let me pause here and see if anyone wants to ask a question. And if no one wants to ask a question, somebody should confirm you can still hear me. Can you hear me?
Yes.
Okay, great. Okay, so I'm going to explain how the simulator for the Sigma protocols actually works. So, and I think this will finally make, I think this discussion thus far hopefully has been somewhat helpful, but, probably a little bit hard to follow. I think this will make things maximally precise. So, the simulator in the definition of zero knowledge is required to output transcripts. That is a sequence of messages, purportedly exchanged by the prover and verifier. But it's, the transcripts themselves, the protocol itself happens in rounds. Like, the prover sends a message, the verifier responds, the prover responds to that. The transcripts are just static, right? It's just like a list of it's a non-interactive, like, list of those messages. And so the simulator has the ability to kind of choose the transcript out of order. All right. So in particular, the simulator for these Sigma protocols will work as follows. It'll actually choose like R and M2 first. And then together, like, it'll choose R at random and maybe M2 at random as well. I forget offhand. And then once you choose R and M2, there'll be like a unique M1 that makes it, completes this into an accepting transcript. Okay, so this is like the reverse order compared to what the actual prover has to do, right? So the prover, in the actual protocol, has to send M1. Only then does it learn, like, the random challenge R, and does it have to then come up with M2. Okay, so the simulator has this extra power that the prover itself does not, to kind of generate later message in the protocol first and sort of backfill the earlier messages to make things look right. What I guess once I hopefully, now that I've explained that that's how the simulator works, it should be really clear that, like, the existence of the simulator does not give you a successful cheating prover strategy, right? The prover has to send M1 without knowing R. The simulator can choose M1 after choosing R. And so you can't, like, take this, if you're a cheating prover that doesn't know a witness, it's not going to be helpful to have the simulator. You can't, like, use it to, do anything helpful, really. You have to, as the prover, choose M1, and then you're stuck with it, right? The simulator is going to choose R and M2, and only then decide what M1 should be. Okay, questions? All right. So it is a very subtle notion. I think if you haven't seen the notion of a simulator before, like, you're gonna get yourself confused. I actually regularly get myself confused even today. And the way that I tend to unconfuse myself is to consider, well, Sigma protocols, I think, are nice, clean examples. And we'll discuss those in detail probably next meeting. But the other protocol I keep in mind to unconfuse myself, and I think it's a nice, clean example, is I'm going to cover shortly. But before I cover that protocol, I want to now discuss variations on the definition of ZK, right? Because I said like the definition of the simulator I gave to you is not totally formal yet. And the reason it's not is because I haven't said what indistinguishable means, right? So I required that the output of the simulator, like the distribution of outputs of the simulator, should be indistinguishable, whatever that means. So I'm about to tell you what that means, from the messages that the verifier sees when interacting with the honest prover. So what does indistinguishable mean? So there's actually 3 different versions that make sense to look at. So one is literally the same. So the distributions are equal. Okay. In that case, this is called perfect zero knowledge. Okay. And in fact, all snarks have this property. All practical snarks like today have this property. Now there are some like weird subtleties about when snarks derive from fiat Shamir and like what it even means to be zero knowledge when you got random oracles around that are really instantiated by concrete hash functions. And let me ignore those issues right now. So let's just say, all practical snarks are perfect ZK. So you don't actually have to know anything about the other 2 variants of indistinguishability after today, but I think it's definitely worth discussing them today. Then you can forget about them. So the other 2, one is called statistically indistinguishable, and the other is called computationally indistinguishable. So computationally just means sort of what it sounds like. If any polynomial time algorithm, the 2 distributions look the same roughly. So the way that gets formalized is, you can have an algorithm that's like trying to guess, like, am I seeing a draw from, one distribution or the other, right? And the distributions are said to be computationally indistinguishable if for any efficient algorithm, like it sort of doesn't have any, advantage over random guessing when it tries to, distinguish the 2 distributions. Is this a draw from distribution A or distribution B? It might as well just toss a random coin. And statistically indistinguishable, it requires that, like, even if that algorithm is inefficient, it still can't do much better than random guessing. So perfect ZK would say that the algorithm literally cannot have any advantage at all over random guessing, no matter how long it runs, because they're literally the same distribution. So of course, any algorithm is going to behave the same when run on, a random draw from the 2 distributions. They're the same distribution. Statistically indistinguishable says, no matter how much time you give the algorithm, it can't do much better than random guessing. Computationally says, well, if you give the algorithm enough time, it could do better. But if you, insist that the algorithm not take that much time, it can't. Okay, and so let's see. What do I want to say next? Okay, so those are variations of indistinguishability. Let's briefly talk about 2 other, another axis where there's variation. So this is honest verifier zero knowledge versus dishonest verifier. This is just getting at what I was talking about earlier, whereby once you start considering zero knowledge, it makes sense to think about verifiers that might deviate from the prescribed protocol, sending like challenges to the prover that they really shouldn't be sending, in order to try to trick the prover into leaking information about the witness. And so, we call, like a cheating verifier a dishonest verifier here. But if we just assume that the verifier is not going to deviate from the prescribed protocol, we call that, as long as you're zero knowledge for that verifier only, we call that honest verifier zero knowledge. Now in snark land, because the proofs by definition are non-interactive, there's actually no room for the verifier to deviate from the prescribed protocol. So this distinction is like just doesn't parse. So it's like it doesn't come up in snarks. Okay, but what's going to happen is the way our snarks are designed is we're going to wind up like kind of developing an interactive protocol, typically, not always, but an interactive protocol that's honest verifier, zero knowledge, and then render the the interactive thing non-interactive with fiat Shamir, and that sort of forces the verifier to be honest because it eliminates the ability of the verifier to even send a challenge to the prover. The whole point of fiat Shamir is to kind of take the interaction out of the protocol. So as long as the original interactive thing was honest verifier, zero knowledge, kind of intuitively, the fiat Shamir version should also, be kind of dishonest verifier, zero knowledge, since, fiat Shamir kind of, in a sense, automatically insists that, the quote verifier challenge in the protocol is honestly generated because it's like the output of the hash function. And we, kind of think of these hash functions as kind of totally unpredictable, spitting out uniform random outputs, something like that, exactly as the honest verifier would behave in the interactive protocol that we're applying fiat Shamir to. Okay, so those are the main variations of zero knowledge. So while there are 6 different variations here, 3 choices for indistinguishability and 2 choices for honest or dishonest verifiers, for snarks, you only really have to worry about one variation, perfect ZK, and there is no distinction between honest and dishonest verifiers. But just to continue the theme of sort of a combinatorial explosion of variations on kinds of protocols, remember there are 2 different kinds of soundnesses that we consider. There's computational soundness, which refers to argument systems. They use cryptography, and if the prover can break the crypto system, it could potentially, find convincing proofs of false statements or whatever. And then there's statistical soundness, which is what we call proof systems instead of argument systems. Although, people do regularly sort of more informally use the term proofs also to refer to, argument systems. So sometimes the word proofs formally means statistically sound, and other times it doesn't. But anyway, and so once you start having, this really creates like 12 different kinds of protocols, right? Because there are 3 choices for what indistinguishability means. 2 choices for do you have to be zero knowledge against only honest verifiers or also dishonest ones, and then kind of 2 different choices for soundness. So that's like 2 times 3 times 2 is 12 different possibilities. And so I do want to flag that if you don't just look at the snark literature, but look at the cryptography literature and zero knowledge more generally, there actually are, like 12 different kinds of protocols that people wind up studying. And it can often actually be very difficult to tell which kind of protocol they're studying without reading like quite deep into the paper. So I guess I just wanted to mention that. There are plenty of theory papers that will look at, statistical soundness and computational zero knowledge. And they will just call those zero knowledge proofs. And that is really like a correct meaning of the term zero knowledge proofs, because statistical soundness is what you should call proofs. And computational zero knowledge is a version of zero knowledge. So those papers will say zero knowledge proofs, and you're like, well, people also call snarks zero knowledge proofs, and those are computationally sound and perfect zero knowledge. So hard to tell, what they mean. So just flagging that. And then the other reason I'm bringing up all these variations is because the protocol I want to tell you about today actually is a statistically sound and also honest verifier, perfect zero knowledge. Okay, and so protocols that are statistically sound and also like statistically or perfectly zero knowledge Those are referred to as statistical zero knowledge proofs, or SZK. So this means like both ZK and soundness are statistical, so neither is computational. Yeah, that's what SZK stands for. Okay, and it's like widely believed that SZK is does not contain NP complete problems. So we're never going to show that until we show that P doesn't equal NP. But let's just say like almost certainly SZK does not. Like there are not efficient SZK protocols. So not efficient. No efficient SZK protocols for NP complete problems like circuit SAT. Okay, so the snarks we use in practice, they're for circuit SAT or generalizations thereof, and we really think it's really essential that at least one of soundness or zero knowledge be not statistical, but rather computational, in order to give efficient, proof or argument systems for that problem. And with snarks, what's going on is the soundness is computational, and the zero knowledge is perfect. It's which is even better than statistical. So these SZK protocols, we don't. I'm not bringing them up because they're useful in practice. I'm bringing them up. I'm going to tell you one SZK protocol, and it's nice and clean. And I think it's just a good example to have in mind if you ever get confused, like, why is there not a contradiction between the simulator I just described and the soundness of the protocol? I think this is a good protocol to go back to and, clarify by example why there's no contradiction there. I just briefly mentioned as an aside, SZK protocols do play an important role in cryptography. This is basically because while we don't think SZK contains NP-complete problems like circuit SAT, we do believe it contains problems that are not actually solvable by efficient algorithms. And so there are a lot of crypto systems actually that would are based on the assumed intractability of problems that do have efficient statistical zero knowledge proofs. So it's just this very interesting class of problems that is presumably much smaller than NP, but does seem to contain problems that are hard enough that you can like base crypto systems on their presumed hardness. It especially contains a lot of lattice problems. So trying to understand better, like just how hard are some of the problems that have efficient statistical zero knowledge proofs is like a really fascinating topic in like theoretical cryptography, which I like it a lot. I think it's just really beautiful. So that is a reason cryptographers in general should care about SZK, but I don't think the snark people should not. It's just you have to allow the soundness to be computational if you really want to get practical protocols here. Okay, so let me just pause, see if anyone wants to ask a question. If not, I'm going to give the one example for today, which is an SZK protocol for something called the collision problem. Yeah, but let me pause here. Does anyone want to ask anything?
Yeah, hi.
Hi.
New here, by the way.
Welcome.
Thanks. You mentioned, I might have missed this, but you mentioned that all snarks are or have perfect zero knowledge. Is there a reason why this is true?
Yeah, I would say it is because the techniques that are used to to endow snarks with zero knowledge just naturally have the zero knowledge be perfect. Let me say a word or two about how this is achieved. Typically the right way to get a ZK snark is to design a snark that's not ZK, like just don't worry about ZK, and then like do a little extra work at the end to turn it into a ZK one. And like one example of how to turn it ZK, is not the only example, is to do the following. So take the messages the prover would send in the non-ZK protocol, and rather than have the prover like literally send those messages to the verifier, instead have the prover send what's called a perfectly hiding commitment to those messages. And so conceptually, you can think of that commitment as like a locked box, and the actual message is like inside the box. But when the verifier just receives this locked box, it doesn't actually learn anything about what's inside of it from the box, the outside of the box itself. And then later, the prover will prove using like a specialized zero knowledge protocol that it knows how to open the box to a message that would have caused, the original non-zero knowledge, like verifier to accept. But that proof itself, that it could have opened the box to something convincing, will also be zero knowledge, like perfect zero knowledge. So in the end, the verifier learns nothing at all about what's in the box. So hopefully that makes a little bit of sense. We'll actually see that transformation in full detail probably just in a few sessions from now. But yeah, like, so the cryptography is just making everything perfect zero knowledge. Like these commitments just reveal absolutely nothing about, the committed messages sort of inside of them. And so the verifier never learns anything at all. Was that helpful?
Yeah, that makes sense. You can have like masking polynomials.
Yeah, it's all masking. So in a sentence, it's just you mask the actual messages that like the non-zero knowledge prover would send, and so it's perfectly masked. So everything's just uniform random in the end.
But theoretically, you could have a snark that isn't. But I guess that's not useful if you can just get perfect zero knowledge.
Yeah, exactly. So it's like the techniques that are most efficient to turn these things zero knowledge just like hand you perfect zero knowledge like automatically anyway. But yeah, in principle, you could have a snark that's not perfect zero knowledge. And there would be obviously generic transformations from that non-perfect zero knowledge snark to a perfect zero knowledge one. Those transformations look a lot like what I just described to you. So in principle, someone could cook up a non-perfect zero knowledge snark. Sure.
Thanks.
Yeah, thanks for the question. Let's see if there's anything else I want to say about this, actually. Yeah, I'll leave it there. Anyone else want to ask anything? Cool. All right, so let's talk about this collision problem. Now, I'll warn you, this is a pretty esoteric problem. Like, you're not, this is not the protocol that like most courses that cover zero knowledge like show people as a demonstration of like the interesting zero knowledge protocols. But I think it's a great example. And it does require a little bit of, it might feel a little artificial, the problem. But I'm just going to define it. And I, last night when I presented it, it seemed to go over well. So let's just dive in. So let's say the input for the verifier is a list of n numbers, say x1 to xn. Say each number is in, it's just an integer between 1 and r. And let's actually say that r equals n. But it's going to be just helpful to keep them as separate, notationally. You'll see why. There'll be, like a part of the protocol will require the prover to send the verifier to send like a random range element to the prover, and the prover to respond with a random index into the list. And using different letters for the size of the range and the size of the list just, clarifies, are we talking about like a random range element or an index into the input list? Okay. And so, the goal for the verifier is to determine whether every range item appears at least once in the list. Right. And if R and N are the same, then every range element appearing at least once in the list is equivalent to the list just sort of being like a permutation of the range elements. That is, just by sort of some pigeonhole counting thing, like if any range element is like ever duplicated, like then you sort of don't have enough list elements left over to include everyone else. So, if the answer here is yes, then what I'm saying is every range element appears exactly once in the list. Okay. And so another way to, just view this problem is you can think of the input list as the evaluation table of some function. So, if the function has domain size n, then this is just a list of all evaluations of the function across like every domain item. And the question then is like, is the function injective? So is the list, another way of asking the question is the list, the evaluation table of a bijective function? Okay, so that's what the verifier sort of wants to determine. But now I'm going to add a wrinkle here. So suppose, and this is where the problem, gets a little bit artificial. Suppose the verifier knows, is promised that if the answer is no, then actually the input is sort of very far from being bijective. So that is then at most, let's say 1/2 of the range elements appear at least once in the list. So, there's sort of, the verifier is sort of guaranteed that, just we don't have to worry about what happens if the verifier is fed an input that is sort of, not bijective, but like somewhat close to being bijective. Like we're only worried about what happens if when the input is either a bijective function or like nowhere near a bijective function. Okay. Okay. Any questions about that? Cool. All right. So it's actually known unconditionally what is the fastest possible algorithm for the problem if there is no prover. If the verifier wants to solve the problem on her own, the algorithm runs in square root n time. Okay, and what it does is it just randomly samples about square root n list items and checks, let's say distinct list, like it doesn't sample like x1 twice ever, so it'll pick root n. There's no reason to ever, look at the same item twice. So yeah, picks root n, distinct list items and looks to see if there's a collision in the sample. Okay, and this is completely equivalent to something called the birthday problem or birthday paradox, which basically says, okay, so if it's a yes instance, so if x1 to xn is a yes instance, so it's bijective, there will never be a collision in the sample. The probability that you sample like an xi and an xj such that xi equals xj it's just zero, because every single list item is different, right? So you'll never get an xi and an xj that are the same. There will never be a collision in the sample, right? By collision, by the way, I mean just like an I and a j that are not the same, but such that xi equals xj. Okay, but what the birthday paradox says, and I run through the math in like certain footnotes in the book, but you can just believe me if you'd like, that if the instance is a no instance, so if the input is pretty far from being bijective, then with decent probability, say like with probability at least 4/5 or something, there will be at least one collision in the sample. Okay, and yeah, it's known that this is sort of optimal in the sense that if the algorithm inspects like significantly fewer than root n input items, then even in the no instance, it's not going to see a collision. And in that case, there's literally no way to distinguish, like, whether this is a yes instance or a no instance, because either way, you're just, potentially seeing a list of random numbers between 1 and n that don't collide, none of which collide. They're just, random numbers between 1 and n, no two of which are the same. So unconditionally, it's known exactly what the fastest possible algorithm is for this problem. The algorithm just randomly samples root n inputs and looks for a collision. Collision is like definitive evidence that it's a no instance. But if it inspects fewer than root n items, it's very unlikely to get that definitive evidence, even if it is a no instance. Okay. Now this collision problem, like, I said, it's a little artificial, but it actually was brought up to model something that is not at all artificial. So, like a major problem in cryptography is like finding collisions in hash functions and cryptographic hash functions, right? So like a lot of our snarks might be totally insecure if we wind up using a hash function where one can efficiently find collisions in the hash function. And so this collision problem is some kind of, kind of stylized variant of finding a collision in a hash function. So here we're saying, look, think of x1 to xn as like all possible evaluations of a hash function like SHA or something. And we're just we're just asking for the algorithm to distinguish the case from there is literally no collisions at all because the hash function is injective, from the case where there are a bunch of collisions, because it's very far from injective or something like that. And this lower bound I told you is that, like, if you really do model the hash function as like a random oracle, like totally unstructured, then there is no efficient algorithm for distinguishing these two cases. The best you can do is times square root n, where here n is remember the size of the output space for the function. And for most modern hash functions, right, like that the size of that output space would be like 2 to the 256. So square root of that would be like 2 to the 128. And so running this algorithm on like a practical hash function would be totally intractable. So this is sort of just saying, like, without exploiting like some special structure in your specific hash function, if you just really treat the hash function as like some kind of random oracle to completely unpredictable outputs, there is just no efficient procedure, just like unconditionally, to find a collision, or even to distinguish, like, a case from the hash function literally not having any collisions, from the case that there are a lot of them. Now, of course, real hash functions are not random oracles, and so this is by no means, this basically says nothing about the hardness of finding collisions in like SHA itself. Anyway, so this problem, while a little bit artificial because of this weird promise, that either the input is bijective or else it's very far from bijective, it is sort of in the league of something that is in fact very natural and central to cryptography. Okay, so that is the collision problem. That is the fastest possible algorithm to solve the problem if you do not have access to a prover. Now let us talk about a zero knowledge proof system where the verifier is going to be like vastly faster than square root n time. So the prover will be like saving the verifier tons and tons and tons of time compared to if the verifier had to solve the problem on her own. Okay, so this is going to be an honest verifier, perfect zero knowledge protocol for SDK for the collision problem. And it is the verifier. Well, I'll just sketch the protocol now. The verifier is going to send to the prover actually a randomly chosen range element. So that's just one number between 1 and r. The prover is going to respond with a certain index I. The verifier is going to check that the ith input xi equals r, except if so, reject otherwise. And so the verifier time here, it's just reading two numbers between 1 and n and inspecting one input. There are n inputs in this list, and the verifier is only going to look at the ith input in the list. So the verifier time is constant. So the verifier time here is going all the way from root n down to 3 or 4 or something. So the verifier is saving like an enormous amount of time by getting access to this prover, who is willing to take the time to like read the entire input list, but is not trusted. Okay. Any questions at this point? Okay. So we have to explain that the protocol is complete. And I'm going to say a little bit more about how the protocol works in case I was too quick before. We have to show it sound, and we have to show that it's, honest verifier, perfect zero knowledge. Okay. So yeah, what's happening here is the verifier, the honest verifier, sends a random range element to the prover. The prover is, if the prover itself is sort of honest, follows the prescribed protocol, it sends the I, which, the prover here, remember, is claiming, sorry, let me be clear. The prover is claiming that it's a yes instance. So x1 to xn is a yes instance. Right. So if it's a yes instance, right, then every range element appears at least once in the list, x1 to xn. So there will always be some I such that xi equals r. And so, the prover sends back that I, and the verifier just confirms that indeed xi equals r. Okay, so that's just sort of explain completeness, right? If it's a yes instance on any yes instance, and for any verifier challenge R, by definition of yes instances, there is some I that the prover can respond with such that xi equals R, and hence the verifier will accept. Okay, so that's completeness. Soundness is the following: on any no instance, because of this weird promise that says, the only no instances we have to worry about are those where at most half of the range elements appear in the input list even once. The probability that, over the random choice of R, that there is some I that the prover can respond with that makes the verifier accept, that is xi equals R, is at most a half. Just because, the definition of, the promise is that at most half of the range elements have such an I. And so, if the verifier happens to pick a range element that does not have such an I, there's just no response the prover can give to make the verifier accept. Okay, so, in general, we don't like soundness error a half in our protocols. We like it to be, like 2 to the minus 128 or something. So one could drive the soundness error lower by repeating the protocol many times. I'll flag that there are some weird subtleties that come up where you can take a zero knowledge protocol and like repeat it many times, and depending on how you do the repetition and things like that, you might, for very counterintuitive reasons, potentially like lose the zero knowledge property. But let's just not worry about that today. Let's just be happy with soundness error half. Okay, so completeness and soundness are pretty easy here. So the interesting thing is showing that the verifier learns nothing from the proof, from this I. Okay, let me just pause. Does anyone want to ask a question? Okay. So I think it's worth mentioning, if the verifier is dishonest, it actually can learn something from the prover's message. So this really is only honest verifier, perfect zero knowledge. So what a cheating verifier could do is pick, rather than picking R at random from the range, right? It could pick some range elements that it chooses non-randomly, and that then the prover will wind up telling it an I such that xi equals R. So in like the hash function application, this is like a verifier that wants to learn a preimage of a certain hash value can just send that hash value to the prover, and the prover will happily tell it the preimage. And that's not information the verifier could have computed on its own. So somehow it's only like the fact that the verifier has, if it's honest, has no control over R, that R is chosen at random, that ensures that the verifier learns nothing from I, other than, of course, that the prover's claim is true, namely that x1 to xn is most likely is a yes instance up to the soundness error a half. So what's going on is, let me just think for a second if I should just give you the simulator or if I should give some more informal thing. Maybe I just give the simulator and then I'll explain. I'll just babble a little bit about various ways to think about the simulator. So here's the simulator. The simulator will just output. So remember, it has to output a transcript, right? And like the real transcript generated by the verifier and prover has the verifier pick R and the prover respond with I. But the simulator can choose the transcript out of order, and that's what it will do. So it will pick an I at random, from 1 up to n, which of course n is the same as R, but yeah. And it will just, the simulator will make one query to the input to learn what xi is, and that's what it'll set the challenge to be. Yeah, so if I tell you on a yes instance, if I tell you what R is, there's a unique response that will convince the verifier to accept I. But similarly, if I tell you what the response I is, there is a unique R that the verifier could have sent that would have caused I to be accepted. And that's sort of what the simulator is exploiting here, is kind of the latter view of things. And the point here is that if we are running on a yes instance, so running on a yes instance, it's sort of equivalent to choose I and then set R to be xi as it is to choose R at random and then set I to be the I cars such that xi equals R, right? So if we're on a yes instance here, the prover and verifier generate transcripts, of the form, R comma, I want to say, okay, yeah, like, all right, they generate transcripts of the form xi comma I, but where, v does not know I when R is chosen, because R is just chosen to be a random range element. But either way, and the simulator chooses, transcripts in this exact same way, xi comma I. It's just the simulator does know, unlike the verifier, the simulator does know I when xi is chosen. Okay, so the transcripts spit out are literally the same. The simulator spits out the same distribution over its perfect zero knowledge. Honest verifier, perfect zero knowledge. It's the same distribution of a transcript spit out by the simulator as the distribution produced by the prover interacting with the honest verifier. Now, in both cases, it's xi comma I for a random I. It's just the way the transcript is chosen with prover and verifier is sort of feels reversed. The verifier picks R at random. It doesn't know which I satisfies xi equals R, and the prover then tells it. Whereas the simulator picks I at random and then sets R to be xi. Okay, and so what's going on is if the verifier actually has no control over R because it's selected at random because the verifier is honest, then what it learns from the prover is just completely the same as if the verifier picked I at random and queried the ith entry of the input list, right? So again, if the verifier was dishonest and it could select, it had control over R, it could learn a pre-image, it could learn the I that corresponds to that R. But if the verifier is honest and doesn't have any control over R, then the verifier doesn't learn anything that it couldn't have learned just by picking, like querying a random entry of the input. Yeah, so that is this HV PZK protocol. let me pause here. I think there's a maybe one or two extra points of discussion worth bringing up, but it's not nice, clean protocol. And sort of the simulator is like kind of simple as can be. And I sort of told you with the Sigma protocol is like the way the simulator is going to work is by kind of choosing the transcripts out of order. Later message is chosen first, and then sort of backfilling the earlier messages. Here you see that like in action, which is a reason I like this. It's sort of a simpler setting to see that simulation technique going on. Anyone want to ask anything?
Can you define the witness in this?
Yeah. Okay. So, great question. I was kind of hoping no one would ask it. So, the zero knowledge, proofs and arguments like make sense in multiple contexts. There is no witness here. So you can apply a zero knowledge, proof or argument system to just like a problem that's hard to solve. The prover is not claiming to necessarily know a witness. It's just claiming like the answer to this hard problem is blah. And there are other contexts where like a witness always exists and the prover's claim is only interesting if it actually knows the witness. So this is a context, this is like the former situation. So this is where this is just a hard problem to solve. To solve this problem from scratch, you need root n time, where n is like the size of this input list. And the prover's claiming something about the input list, which takes a lot of time to compute and is convincing the verifier that the claim is true. So it's not claiming to know a witness here. It's just claiming something about the input list that takes a lot of time to compute and is going to save the verifier the work of doing it. So the relevant security notion here is what's called standard soundness. It's just if the answer is no rather than yes, the prover will not convince the verifier except with small probability. With something like a Sigma protocol and in snarks and all of that, like the relevant setting is typically in cryptographic applications anyway. What I was saying, where the witness always exists and things only get interesting when the prover is establishing and knows the witness. So this is you caught me. I sort of was using the language of the prover claiming to know a witness all day, and then I gave you a problem where there just is not a notion of witness, and the soundness we established here was not knowledge soundness. It was just standard soundness. The prover's claim is true. Did that make sense? Cover my tracks acceptably?
Yeah. In the case that there's no witness, is the simulator always like, or like is it always really easy to get zero knowledge because like the simulator just does what or it seems pretty trivial to like define a simulator.
Yeah, I mean, this simulator is like as simple as it gets, but actually is like somehow somewhat deep because look, I mean, Sigma protocols are simple too, but like they're also like awesome, and there are practical signature schemes that are derived directly from Sigma protocols and stuff. And the simulator there is like doing something completely analogous to this. This is just a simpler, cleaner setting to make it feel completely trivial almost. So let's see what I want to say. I don't think it's the case that giving a simulator is like always trivial when there's no witness. But there are fewer example protocols to like tick through in my mind at the same time. So the typical like first zero knowledge protocol covered in courses is a protocol for graph non-isomorphism. And there, I'd say the simulator is also pretty trivial, but like it's exploiting like some other power that the simulator has that the actual prover does not. In that case, the protocol is private coin. So the verifier has some like secret it's keeping from the prover. And the simulator is allowed to know that private coin. And I can actually sketch that protocol in sort of cartoonish form right now without any math. It's just the idea of the prover, claims to be able to tell Coke and Pepsi apart. And the way this gets proven is by the verifier sort of, picking Coke or Pepsi at random and filling up the glass, with either the Coke or the Pepsi behind its back. The prover doesn't see it, and it hands the glass to the prover, and the prover, says Coke or Pepsi. And if the prover can't tell them apart, then all it can do is guess. But if it can tell them apart, it'll get it right every time. The simulator there is just the one that picks Coke or Pepsi at random, knows which choice it was, and outputs, so picks Coke or Pepsi and then outputs the response, whatever it picked. If it picks Coke, it outputs Coke. If it picks Pepsi, it outputs Pepsi. So that's like another trivial simulator, but it's sort of exploiting something else here in terms of the power of the simulator that the verifier doesn't have. Trying to think if there are, in terms of non-cryptographic stuff, I actually don't even have cached all that many other example protocols. These SCK and HVPZK classes, they contain some interesting problems, but just there are like a handful of canonical examples. I don't think the list is that big to tick through. So I'll kind of leave it at that. I guess I'd say that you might be viewing this simulator as like a little more trivial than it actually is. Maybe I'll leave it at that. But that I do think there might be some more complicated examples out there if one thought enough about it and thought through enough different example problems and protocols.
Sure. Yeah, that's believable.
Yeah, I'd say for snarks, actually, this, I guess normally the simulator in these snarks is basically just, no, is that true? I take it back. Depending on what technique you use to make the snark zero knowledge, the simulators can also be trivial. I'm pretty sure, right? No, I guess they like almost all of them are based on Sigma protocol somewhere, or masking polynomials. Yeah, okay. I think the simulators like basically always like choose a bunch of messages at random and like kind of backfill the other messages to make it an accepting transcript. I think they like almost all simulators work this way if you're dealing with public coin protocols that get fiat shammired. So yeah, and that's exactly what this example is capturing here, just in like a ridiculously simple setting. So I think in terms of techniques you tend to see in the wild, that is really the main simulation technique. Now, if you go to like theoretical cryptography papers that are divorced from like practical snark design, I don't even know the literature that well, and I'm sure these simulators can get much more complicated.
Yeah, I think in my experience, I've only dealt with simulators that generate random values.
Yeah, exactly. Yeah, and it's kind of like, to me, it's like, well, what else could the simulator really be doing, right? Like the whole point of these snarks, when you do make them zero knowledge, is that like everything should just look random. So obviously what the simulator should do is choose a bunch of random stuff and then like fill in anything else that needs to be like derived from the random stuff. Like what else could the simulator possibly do, right? But I guess it might be a little bit subtle sometimes because like, I know like the original Planck paper had like botched the transformation actually to ZK, and no one picked up on that for several years. So I don't want to make overly sweeping statements here, but I never went and like studied carefully like exactly what the issue was there. I guess it can be a little more piddly than you would like. So it's always there are these like generic transformations that just always work, but like add some concrete overhead that people don't want to pay. And it's always, high level, it's like always possible to like actually add very little overhead when you're making performance overhead when you make things ZK. But in order to do that, it's often like, you do have to do something a little more ad hoc, and now it's error prone, and you might do, if you don't spell out the simulator in full, you might make a mistake and the thing is not actually zero knowledge as you think it is. That's sort of my general sense of how ZK tends to behave in practice. Other questions? Okay, let me just see what other, I think I maybe have 2 more comments to make, and then we'll wrap up. And, I've covered all the content I want to cover. These are just, it's like if you're seeing ZK for the first time, it's like subtle enough, that it's not like contradicting security. That I'm just trying to head off the typical sources of confusion, which I think like even people who have been studying this stuff for a long time fall into the same lines of thought and have to like break themselves out of why there's no contradictions and stuff. So let's see. Okay, yeah. One thing I want to point out, I guess, is I think it's interesting to think about what happens if you run the simulator on a no instance. Maybe this is the last thing I want to say. Let's just think about what happens there. So in that case, remember what the simulator does is first it chooses I, and then it sets the verifier challenge to be xi with like one query to I. Okay, so in a no instance, like the input is still like a list x1 to xn. It's just most range items don't appear even once in that list. Okay, so this simulator is always generating a transcript of an accepting interaction. Okay, so even though like the actual prover can, sort of have probability at most a half of convincing the verifier to accept, the simulator is nonetheless always spitting out transcripts that do lead to acceptance. Okay, and of course there's no contradiction here because the simulator is able to choose I and then choose xi, whereas the prover is handed R chosen by the verifier. The prover has no control over R and has to respond with an I such that xi equals R. So just pointing out here, there's no contradiction between the simulator's ability to spit out accepting transcripts on no instances and soundness of the protocol. And then I think another thought that I encounter a lot, and actually it's not. Variations of this thought are actually extremely useful in like proving limitations of like statistical zero knowledge proof systems, but we don't have to get into that. There's a question of like, can I try to use the simulator to efficiently solve the problem, without speaking to the prover? And of course, the answer is going to be no, right? Because we have perfect zero knowledge arguments, our zk snarks, for circuit sat, which is like definitely like an intractable problem. We have I told you for this collision problem, like unconditionally no, without access to a prover, it takes root n time. You can't do any better than root n time. But the simulator runs in constant time, right? It just outputs, picks a random I and outputs xi comma I. So, the natural way to try to use the simulator to efficiently solve the problem is to basically like run it a bunch of times, run S a bunch of times, and sort of try to distinguish, like intuitively, like S should behave differently if you run it on a no input versus if you run it on a yes input. So you might try to like, try to distinguish whether its output, is, is sort of coming from, the simulator running on a no instance versus a yes instance, right? So in this example, and I'm just about done here. I know I'm pretty late. In this example, the output of the simulator on a no instance is like very different, distributionally speaking, from its output on a yes instance. Because on a no instance, right, like the xi's it winds up outputting, no matter how many times you run it, you're never going to see all the range items there, right? Because by definition, a no instance, at most half the range items appear at least once in the list. And if it doesn't appear at least once in the list, the simulator will never output that range item. And what's happening is like that actually works. I think it is required ultimately that like the stuff the simulator outputs like looks different on yes instances versus no instances. I have to think that through, but I think that's the case. But what's going on here anyway, I'm sure about this, is it's just the number of times you'd have to run the simulator before you can kind of detect a difference between no instance versus yes instance is so much that the algorithm is not efficient. So in fact, the fastest algorithm for this problem, remember what it does is it picks root n different i's at random, queries each xi for each selected I, and looks for a collision. That is literally the same as running this simulator root n times and then seeing if you ever see like the same xi twice. Okay, so you actually could try to use the simulator to solve the problem without access to the prover in the way I described, just like, run it over and over again, with different fresh randomness each time on your instance, and try to distinguish, its outputs from like, outputs it would run if it would spit out if it is run on a yes instance versus a no instance. But what's going on is it just might take a whole lot of runs of the simulator to detect the difference. And so there is no contradiction again. It's like this algorithm might actually lead to the fastest algorithm for the problem, but it's still not a fast algorithm at all. Okay, so I think that covers most of the ways, people seem to initially think that the definition of zero knowledge is somehow in conflict with either soundness of the proof system or intractability of the statement being proven. It is in fact not in contradiction with any of that, but it is very subtle, so like knowledge soundness as a notion of security literally requires that one can take the prover and pull a witness out of its head. It's just the extraction procedure is, that pulls the witness out of his head is sort of allowed to do things with the prover that the actual verifier is not able or allowed to do. So there's no contradiction between, the verifier learning nothing about the witness and the extractor literally identifying the witness. They're given different kinds of access to the prover and stuff like that. Okay, so I hope this was helpful. Happy to answer questions if there are any, but if not, then keep an eye out on the Discord because I could have a newborn any day. I think it'll be another couple weeks, but you never know. So I'll keep you all informed. And assuming we do meet next week, I think we're going to start talking about Sigma protocols, which you got a preview of today, and which are really really cool and beautiful. So yeah, let me know if you have questions. Otherwise, thanks for your time, and I'll see you next week.
Thanks. See you.
Yeah,
Thanks
thanks
so
Ethan.
much.
Yeah, have a good one.